we are going to check out a couple of these Matlab tutorials. So again, here's the order to take a look at them. They'll be in Oaks numbered this way. So the first one, Matlab tutorial 1, let's go ahead and open that file. And this is created by Dr. Newman. 9 pages of just basics. So now that you've gotten Matlab, you want to go ahead and start figuring out how to use it. And you can do just basic computation. You can compute signs and add things, subtract things. Here's our usual arithmetic operations. Addition, subtraction, multiplication, division, exponentiation. So multiplication with a star, division with a slash, exponentiation with a caret. So, common, most math software uses those. How to save and reload work if you want. How to get help on different commands. So there's a lot of built-in commands that we will use. Sometimes you'll be coding and making your own programs or files. Plenty of demos as well. How to get to those demos. And here's a key thing. If you're first time learning how to program, you need to know how to kill a program. So if you've done something wrong, made a mistake, you're in an infinite loop, it's Control-C in MATLAB like it is in the other languages. Lots of resources for MATLAB. It has a whole community. And lots of books and software about it. But these are some nice short tutorials built just for, in particular, the commands we'll need. So next thing I want you to do is take a look at number 2 in MATLAB tool. This is just to figure out how to enter some things. On the left is like if you want to put a row vector, you can do it with commas or spaces, and then the output what it looks like. Column vectors, matrices, to do a transpose, to enter zeros or ones, column or row vector of all ones. So I want you to work through these. There's some short little exercises and practice those. So let's do a few things here. Let's open that up. So I'm going to clear the window. So this is what it would look like when you're entering. You're opening it up. And if you want to, let's say, make a row vector C, and let's make it 1, 4, minus 2, 7. So that displays it, and then notice over here it is stored. C over in your workspace. If you want to turn maybe default C1 and the transpose of that, if you want to turn that into a column vector. If you want to access, let's say, just the first 2 elements of C, you say we don't just see it as another variable. We would say, let's look at indices 1 through 2. I can make a matrix. Let's say 1 through 3, 4, 6, 7, 4, 5, 6. And if I want to know the dimensions of that, it's a 2 by 3 matrix, which is also shown here. If you want to save A, let's make another one. Make B be a matrix 1, 2, 3, 4, 5, 6. This is now a 3 by 2. If I want to create it and save it in the workspace, but not display it, I can do that. Suppress the output with a semicolon. I could try to add A and B, but from linear algebra, it doesn't make sense. But the size of B is 3 by 2, and the size of A is 2 by 3. So we could probably do A plus B transpose. And again, if you want to store that somewhere, C equals A plus B. Capital C is different than lowercase c. And now we've stored it. You can access the previous command you've entered and say change them if you wanted. If you want to go in and change the element, you can do it that way. think those are the main things. Oh, and then help linprog. This is a command we're going to use often. Or how about when we've done some linear algebra, RREF, row reduced echelon form. And it gives some information about that. So I could do RREF of a matrix. So R equals RREF of A, puts it in row reduced echelon form and saves it. Again, we're going to use linprog on that, so you can look at the command here. There's all sorts of information. Linprog is a much bigger help file, but let's actually go to a better way of finding help on any commands or files. Is up here in the search bar. What opens up then is a help page, different information about it. Let's go to the first one, which is the command for linprog. This solves linear program problems. Yeah, that's what we need. Plus, here's the syntax, all the different ways that you can enter it. Here's the general form. We usually set C transpose X, but this is F transpose X. So F is going to be F transpose is a row vector. F will be a column vector. We have AEQ is for any coefficients pulled associated with the equality constraints. BEQ, A less than or equal to B. We need to transform all of our inequalities into less than or equal to, but no problem. We'll do that with some examples. You can have lower bound and upper bounds, like maybe it needs between 0 and 1. Think about a discrete optimization binary integer linear program where it could take on the values only 0 or 1, but if we relax that discretization and just solve, instead of solving the BL, we solve the relaxed LP, we have the lower bound of 0 and upper bound of 1. Okay, so again, lots of examples shown. This is a very big help file. I want to show you a few things at the bottom. Here's some different options that you can play with. You can change the algorithm that's being used. We're going to learn how to do both the simplex and the interior point. The dual simplex is a variant of the simplex. You can say how many iterations you want it to run for the interior point method, which is a heuristic reflection algorithm. And some specifics about the sort of output that you can display, the type of algorithm that's being run. It'll actually give you details about that algorithm, which is helpful if you continue on and do some research. And then it'll also have the references for it. There's lots of graduate students in mathematics at the master's and PhD level are hired by MathWorks, and they're constantly being in literature and trying to implement the newest, greatest, most efficient algorithms. Another thing to see also, this is int-linprog. That's for our integer linear programs, mixed integer linear programs. So we'll see some more of those, but you could solve a binary integer linear program with this built-in command using this syntax. Okay, what else? Okay, so you're going to go through the Matlab tour, do that, and you're going to just keep entering things here in your workspace. You can then print. If you print, you can print it, press print to the PDF, and that will print pages all the pages of information that were in your command window. So that's a way for me to see how you interacted with the tutorials, how much time you spent with it. And that's what you'll submit at the end of the MATLAB lesson as your homework. So you'll print your command window and show that you've been learning and playing around in MATLAB. Okay, let's go to the next one. MATLAB tutorial 2. Okay, this is for programming, and you will, in one of your team assignments in, I think module 5, module 5, you're going to program the simplex as a team. And so this has some details about just making basic, what are called M files. When you store something in MATLAB, you make an M file. So this is a good place to come if you need to review your programming, don't know much about it, don't remember your Math 245 and 246 class. This is a nice, plenty of details in this file, and you can just practice making these information about for loops, while loops, switching. But check that out. That's a pretty extensive tutorial. 46 pages. It's a good reference for you. Now the linear algebra tutorial. This is a good bit of information. Same professor here. All the things that you might need in linear algebra So some commands, pretty much anything you want to do in math, there's probably a built-in command in MATLAB for it. Or if MATLAB doesn't have it, there's a whole community in the MathWorks community where different researchers and professors might, if there's an algorithm, you're like, hey, I remember learning about this in graduate class, someone's probably coded an M file for it. So just Google it. Like here was that RREF we've done. Oh, he's going to type in RREF. To extract just the upper triangular part of the matrix, you could do try-L. To get just the upper triangular, try upper. Okay, and then here's what we did with vectors and matrices. So this is a good place to just go through, review some of the things we just did, how to enter them, and manipulate them. 3, 2, 3, 3, 3, 4, 3, 5 of this document and those examples. How to pull off submatrices from something. Oh, and we forgot to say what the identity matrix is. Let's go ahead and do that back here. If I want to form I is a built-in command, and this will make a 5 by 5 identity matrix. Maybe I want to do call B a matrix, which is 5 times that. Let's say actually 4 times the identity, 3 by 3 identity. And if I want to pull off just a submatrix, I can take rows 1 and 2, colon all. That means colon means all columns. And if I wanted to maybe pull off just the last column, let's say, all rows, 3rd column, and it pulls off just the last column. So you can access any part submatrices within a matrix easily with that command. Okay, I think that's kind of in this section here. Pulling off the diagonal of the matrix. And that's just number B was the 4 times identity right here. So just pulling that off and putting it in back there. You can form, let's see, we had a row vector C, right? You can form a matrix from that by saying diag of C. And it puts those in a diagonal matrix. Should we go through with that? Yeah, solving linear equations. So this is a great thing. If you haven't taken linear algebra in a while, to review different ways of solving AX equal B, it's really nice. You can just use this backslash command. Really what it's doing is Gaussian elimination or REF. It can solve least square systems as well. Some more on RREF. Okay, 3.5, inverse of the matrix. We're going to need that when you're learning both the simplex and the interior point method later on. So this is easy to compute. If the matrix is invertible, it can compute the inverse. Did we have any square matrices? Let's see, A and B, I think, are both. So it's A and B, right? That's easy one. But that was easy one for that one to compute. But it can do inverses of anything if they exist. Let's see, if you asked for the inverse of A, what's going to happen? There, because there has to be a square matrix. All sorts of factorizations it can do. Yeah, determinants. Vector, so that 3, 7 is a good one to go over. Just again, making sure you know how to manipulate vectors, which are just special pieces of matrices in matrix laboratory method. I think the rest of this file though is great, but it's just not stuff that we would need. Okay, so what do we have to do? Linprog and 5. Let's go that. Okay, so this is a short file just saying how to enter a matrix in. Here's a small little example problem. You're trying to maximize 12x1 plus 7x2 subject to these few constraints. Obviously, an easy one that you could solve by hand graphically. It is a linear, so it's a linear program. We can run this with MATLAB's linprog command, and they're showing you how you enter it. So they're pulling off the coefficients of the objective function and putting them in a column vector, 12 and 7. X is the vector of unknowns, so that's what we're going to try to find. X is, and you've decided ordering that it's X1, X2. And then these are all inequalities. And so we're going to put them in the matrix A, and you're pulling up the coefficients again, 2, 1, 3, 2, minus 1, 0, 0, 1, adding up for those, and then your right-hand side. And you just run x equals ln prod f and b. If you also want to get the objective function value, your output is two things: solution vector, which you decide to call x, and the minimum objective function value, which you decided to call f min, and it'll store those. Okay, and it walks you through there, and then there's some practice problems that you can try as well. Okay, the next one, prod, another short tutorial thing. Okay, that took everything in the previous example, did everything in less than or equal to B format. Here, if you have some equality constraints, you need to do it in this next line. You have some inequalities A and B. You have some equalities in the AEQ, BEQ. This walks you through those small examples. You can see the input. This is what you put into Matlab. This is what you get out right here. These are good ones to practice. A little bigger one here. Then just showing graphically, you can check the work on some of these because they're so small. Okay, another nice one here. Nice short one. Let's go to the next one. Okay, another easy one because there's only two variables. You could graphically solve it, but it's definitely a linear program subject to 1, 2, 3, 4, 3 main constraints, 2 simple constraints. And here's how linprod needs to see that these are your input to Matlab. You form these different vectors and matrices, and then you run the linprod command. And there's some practice problems you can try. Okay, next one is the most significant one here. Yeah, 50 pages, but we don't need all of this. This is for a much more extensive optimization with software. This one might be helpful when we get to our programming of the simplex. So you might skim through this one for now, and you may come back to it later. I think this professor built some software to graphically display things, quite a bit of commands there, but just playing with feasible region and the contours, even as a warning that it could be unbounded, and just get that back. A little bit of information about the two-phase simplex here. Okay, so again, this might be helpful for later homework. Just know that it's there. Okay, let's go back and maybe pick an example now. Let's see. Let's look at one page for the text. Page 147. Okay, and there's an example on this page, starts at the bottom of 146. Example 4.1. So some students taking some classes in 4 different classes. She's got 30 study hours to prepare for the finals and wants to divide her time so that she can improve her midterm grades or final grades as much as possible. Her favorite class is OR. She wants to spend as much time on it as any other. She believes up to 10 hours of study in any class, it's kind of what she needs. If she does that, she could get a 2% improvement in OR, a 3% in engineering, 1% in stats, and 5% in material science. Form an allocation linear programming model that's going to help her study. So HI or HJ is the number of hours spent in each course. So there's courses 1, 2, 3, 4, OR, engineering, stats, material science. And then the model is you want to maximize the improvement in your grades, and that's 2% for hours that you spend with OR, 3% for hours that you spend with engineering, 1% for stat, and 5% for material science. You only have 30 hours, so we sum those. You want the OR to be bigger than all the others because again, that's the one she says she'd like to spend as much time as possible. With more time on that than the other. So H1 bigger than H2, H1 bigger than H3, H1 bigger than H4. But they all have to be less than 10 hours. She doesn't want to spend more than 10 in one class. And we're all, this is a typo, it should be greater than 0. It should be non-negative. Can't have negative study hours. Okay, so here's a nice little small enough LP. We can't do it by hand because there's 4 variables. So let's use our course software. So we need to figure out, and let's see, let me use the whiteboard. That's probably the best thing to do. Stop the share. Let's put some stuff in it. Okay, so here's the model. Example 4.1, page 146, 47. Just copied it right here. And then started writing out so we can get it ready to put in our software to solve this problem. So we can pull, let's maybe put this in red. We can pull off the coefficients. We can store those in a vector F. 2, 3, 1, 5. That's the coefficients for the objective function. Then we need to form A and AEQ. Those are our matrices for the equalities and the inequalities. And we have only one equality in our constraints. And so the matrix A for AEQ is just over O vector 1, 1, 1, 1. And the B EQ associated with that is just a scalar. BEQ is 30. Okay, then these constraints, we have some simple constraints and some bound constraints. And so we'll actually write them this way, and you'll see why in a moment, why we're going to write them that way. And they're going to be something called lower bound is going to be put in this vector of all zeros. And upper bound will be put in a vector of all 10s. Again, lower bound and upper bound, we'll explain those in a moment when we get back to MATLAB. And now we need the matrix associated with the remaining inequalities. And so this one was written compactly for j equals 2, 3, 4. So I split that out. H1 is greater than H2. Number of hours on OR is greater than the number of hours on stats. Number of hours in OR is greater than number of study hours in material science. So this one actually splits into 3 separate inequalities. This one says H1 minus H2 is greater than 0, but I flipped that around because the software requires that they all be less than or equal to inequalities. So it's easy to just turn it around, negate this, turns the sign around, makes 0. So same thing happens here. So these 3 constraints combine to make an A matrix, which will have 3 rows and 4 columns, H1, H2, H3, H4. And it'll be H2 minus H1. That represents this one. Now this equation is represented here. 1 minus 1 zeros, and one more H4 minus H1. No H2s or H3s. And then just to make sure on your dimensions here that this makes sense. This is 4 by 3. I'm sorry, 3 by 4. And really you can think of A being multiplied by X, less or equal to B. 3 by 4 by a 4 by 1 of unknowns that we're going to find makes a 3 by 1. So we need one more vector. We need the B vector, and so let's put that. Let's not put that here. The right-hand sides are going to be a vector 0, 0, 0. Okay, so now let's go back to MATLAB and enter that. Okay, so we want to get this model. We've massaged it on the whiteboard into the form that's going to help us put it in MATLAB. So let's go ahead and get that into MATLAB. Let's go ahead and clear. That cleared our workspace out, just clean things up. And if we don't want to see what, if we want to actually start with a completely fresh screen, we can do that, clear the command window. Okay, and so maybe it helps to pull up the LinCrag documentation again, just so we can correspond what we're typing in the command window with what's happening in the documentation. All right, so we have, we're not in the first case. We don't just have inequalities, right? So it's here. We have some equalities and some inequalities. We have some bounds, right? So lower bounds and upper bounds, because we were slamming the x's between 0 and 10. Okay, so we're actually in this case here. And then it just shows you the order that you have to put them in, and this is important. And we define, you can call this anything you want. You can say solution. We use x, y, and a plus, so why not call it x? So I'm just going to copy this, and then we're going to, if I hit enter right now, it's like, okay, I don't know any of these things. I don't know what f is. So we need to start entering this. F is a, just to make sure the dimensions are right. If you look up here, F transpose. So F is actually a column vector, and then it's going to transpose it, make it a row vector times the column vector of solutions. So I'm going to enter F as a column vector. And we had pulled off the coefficients on the objective function where 2, go to the next row with a semicolon, 3, 1. And then you can visualize and see that that's correct. What else do we need? We need A. The matrix A was -1, 1, 0, 0 in the first row, -1, 0, 1, 0 in the next row, -1, 0, 0. Okay, and then its right-hand side was, you can either write it like this, column vector of zeros, or you can say B is zeros, 3 by 1 vector of all zeros. It's the same place. Okay, and then what else do we need? AEQ. That was our equation coefficient, and those are 1 and 1, and there's only one of them, so it's a row matrix vector. And then VEQ was the right-hand side on that one, which was VEQ, which was 30. Oh, and then we need our upper bounds and lower bounds. So the lower bound was all zeros for all 4 variables. So it should be a 4 by 1 matrix of zeros. So we can say zeros, 4, 1. And upper bounds, we can say 10 times the ones. That's a ones vector. Oops. So I did the up arrow to get that from my previous command. Right now, I think we have everything we need in there. A, Q, B, B, Q, F, lower bound, upper bound. And then we can go back to that first command we were trying to do, LinCrag. Okay, and it's saying, here's your optimal solution. If you wanted to output some more information, you can say, what is X kind of objective value. And it says the optimal objective value is 60. You have 6 points of percentage points improvement in your grade if you study in this manner. But there's something funny about this, right? It's saying that don't study it all for, what was the 4th class? Material science, and yet the model said you get 5% improvement in material science. So it doesn't make sense that we're not studying for the thing that's the most, would give us the most gain improvement in our studying. So we must have done something wrong, and it's easy to miss that. What we've done wrong is that it's a minimization. You have to put your problem in terms of minimization, but ours was given as a max. So how do you do that? Pretty simple trick. You just, it's equivalent, if you're trying to maximize something, it's equivalent to minimizing the negative of the objective function. So all we have to do is negate. So we say let f equal negative f, And now we run it. And we will have, now it's saying study 10 hours for operations, which is 10 hours for, so it's optimizing by choosing the upper bound each time. But that's just because it was such an easy problem to make. Don't study it all for stats, and that makes sense because that was the one that only got the least improvement. And overall, it'll give a, remember we're negating the negative, so it's really a 10-point improvement in the objective function value, and that's because you got 5 points for studying for material science, 5 points for studying all that time for engineering, and 5 points for 2 points for OS. So 2 plus 3 plus 5 is 10. Okay, so this tool is a great way to help you practice your modeling. In chapter 4, we're going to do quite a bit of modeling. I think the best way to learn how to model is by doing it. And so you're going to have a lot of team projects where you're going to be working on just discussing, trying to figure out how, is this the right constraint? Did I miss anything? Did I miss any simple constraints? Have I formulated this correctly? The best way to do that is to formulate it on paper and then try to enter it here in Matlab. You could get crazy answers. Sometimes it'll be clear you didn't do it right because it'll say it's infeasible and you know it has to be feasible. Or it'll be giving just bizarre, like some negative answers and you know that doesn't make sense. You need to maybe out of bound. And then again, remember, you can also use int when program if any of the models you're creating in chapter 4 for the upcoming homeworks require integer values. And so do the help up here on int and learn about that. All right, I think that's it. It's really fun modeling. I think there's a real sense of empowerment in making models that actually make sense and realizing how you can use the stuff in the real world. All right, have fun.